So first we start with equilibrium problems. In equilibrium problems, we actually determine time independent, which is also called a steady state spatial distribution of a field variable. Spatial distribution of a field variable. That means here your phi is actually your phi is a function of the space variables and not the time variable. Okay, so the phi is the field variable and the field variable is dependent on the spatial coordinates. So this is a spatial distribution of the field variable. Example is steady state temperature distribution in heat conduction maybe, and steady state temperature distribution in heat conduction problems, steady flow problems like flow over a cylinder, flow over an airfoil, and torsion of an elastic shaft. So these are the cases of equilibrium problems, and many of such equilibrium problems, though not all, many such equilibrium problems are governed by this equation, which is known as the quasi-harmonic equation. So it is quasi-harmonic. Quasi means almost like harmonic equation, but it is not exactly the harmonic equation. So for a homogeneous medium, if your medium is homogeneous, then kx, ky and kz are same all over the medium. But kx, ky and kz, they may be different, but these different values are same all over the domain. And for isotropic medium, kx, ky and kz are same, and that is k, but this k can be different over the medium of the total medium, whole of the medium. So here the boundary condition is defined over the surface, and we have divided the surface into two parts. So two parts, from here to here there is a line is there, and this part, so the surface this part is S1 and the surface this part is called S2, and S1 plus S2 is tau, that is the total surface. You can also call it S. So, and on S1 actually the value of phi is specified. The value of phi, that means on this surface over here, at every point you know the value of phi. And if phi is a specified function, so if you give the value of x, y, z on this portion of the surface, then you get the value of phi. So this is called the Dirichlet boundary condition. And on the other part of the surface S2, this kx del phi del x nx plus ky del phi del y ny plus kz del phi del z nz plus g xyz plus h phi is equal to 0. So this is called a Cauchy boundary condition. So this is the flux term, this is the outward flux. So this much is the outward flux. So this much is the outward flux. So this much is the outward flux. Outward flux. So here the outward flux is specified, and if this G and H are 0, then that is called the Neumann boundary condition. Otherwise it is in its general form is known as the Cauchy boundary condition. Now in the governing equation, in this quasi-harmonic form here, if you assume kx, ky and kz, they are constant and equal to k, kx, ky, kz are constant and equal to k, then you get this equation which is known as the Poisson's equation. And if this f is 0, you get this which is called the Laplace equation. Now we will first derive the finite element equation from the variational principle. So the variational principle corresponding to this governing differential equation and this boundary condition is this. Though this is so, this is the variational principle for the given governing differential equation and the boundary condition. And while, as you have seen in one-dimensional cases, within an element we assume this phi, we replace this phi by an approximation for phi, and we consider that this approximate value of phi, phi e, phi within element e, can be interpolated from the values of the phi's at the nodes. So this is the approximate phi, where this phi is interpolated from the phi's at the nodes. And the total I can also be broken up in i's over elements, and if you sum it over all elements, then you get the total I. Now in derivation of finite element equations, in deriving finite element equations, you take this I as summation of I over all elements, and if you take this variation to be 0, then you get the finite element equations. That means you have to not approximated as, so let me remove this. So 0. So if this is 0, then this is 0. If this is 0, then if this is 0, this implies that this is 0, which you have seen in one-dimensional case. Now first you take an element which is having an edge on the S2 boundary. That means you take an element like this which is having an edge on the S2 boundary. Now suppose you take a triangle element which is having an edge on the S2 boundary. So let us take an element which is having an edge on the S2 boundary. Okay. So del I phi equal to 0, that means del I del phi I equal to 0. So that means, and so I is now a function of phi e. Phi e is the approximation for phi over an element. So within an element I phi is this. So if you take this, so if you take, suppose you just differentiate the first term, and the differentiation of the these two terms would be similar to this one. So we are first differentiating this term, so with respect to phi I. So this is kx twice del phi e del x. So 2 we have written here, twice del phi e del x, and then del phi e of phi I of del phi e del x, because we have to differentiate with respect to phi I, but first we are differentiating with respect to this. So it is 2 into this, then derivative of this with respect to phi I of this, and here this term twice f del phi e del phi I. here G del phi E del phi I, and here half H 2 phi E del phi E del phi. So now if you assume that your phi E is this, then these are the nodal values, and this Nj are function of x, y and z. So remember, this Nj's are actually functions of x, y, z, or the spatial variables. So if that is so, then del phi E del x which we are getting here is del Nj del x phi j, because phi E is Nj phi j. So del phi E del x is del Nj del x phi j, and that's what exactly we have done here. And del phi E del x, that means del phi I of this is nothing but del ni del x. Suppose, for example, here we have shown del phi 2 of this. That means del phi 2 of this. Now, if you take derivative of all these terms with respect to phi 2, only this term remains, and this gives you del into del x. So, this is the case. Del phi I del phi del x is del ni del x. Now, the first term, that is del phi E del x del phi I, this one is the first term. This can be written as, this is the first, this is this, and del phi E del x is this, and del phi I of del phi E del x is this. So this is, if you write this at the front, this is this, and this can be written as a summation like this. So now we can again rewrite. So this is equal to 0 implies that kx del ni del x this plus ky del ni del y del nj del y phi y, then plus kz del ni del x summation del nj del z del ni del z here, then summation del nj del z phi z. So here these are the two terms. So what are the two terms? Here you get, here is actually, let me make it a little thinner. Okay, so let us write it like this. This is ky del ni del y summation del nj del y phi j, which is coming from the second term, and here this term is kz del ni del z, and then summation del nj del z. This summation is actually over j. This summation is actually over j, and this is the other term. Yes, these two terms. So here g ni, and here twice h phi, this is nj phi j, and again ni. So ni nj phi j. So here summation is there. So here you just put a summation sign. Here you put a, where is the thing gone? Yeah. Here you put a summation over j. So now if you take I equal to 1, 2, 3, I actually stands for nodal phi's, nodal phi i's. That means phi 1, phi 2, phi 3, phi 4. So the nodal, if the element has got 3 nodes, then 3 phi i's are there. If the element has got 4 nodes, then 4 phi i's are there. If the element has got 6 nodes, then 6 phi i's are there. So 6 equations you will get. So in the first equation, the first term means you take I equal to 1, then you vary j equal to 1 to number of nodes in the element. So here first take this, that means this, see this term is actually this term into phi 1 plus this term, because del n 1 I equal to 1 here, so del n1 del x, then the summation of, then here there will be summation of this, that means del n1 del x, and then del n1 del x phi 1 plus del n1 del x kx del n2 del x into phi 2 plus here phi 3. But this is not all. Here the second term and the third term will also come. That means this term and this term will also come. So this is the second term and this is the third term. So in this way you can find here I equal to 2. So this, for this I you have to put 2, and then this j actually 1 to number of nodes. J equal to 1 to number of nodes. That means this is 2 and this is 1, here 2, here 3, and this has to be multiplied with phi 1, this has to be multiplied with phi 2, like this. Similarly now here there will be del n 3 del x, kx again del n1 del x, del n3 del y, ky del n1 del y, then again del n3 del z, kz del n1 del z, and in this way it can form this matrix. And this is the second term. So if phi is not there in the term, if phi is not there, see here phi square is there, here phi square is there. If a single phi is there, if a single phi is there in the variational principle, then actually you get a force vector. So this is the force vector, this is a force vector, but here in H there is phi square term. So if you differentiate it, you get twice h phi e l phi e del e. Now for this you get ni, and for this you get summation nj phi j. So here ni, first take n1, then n1 phi 1, n1 n2 phi 2, n1 n3 phi 3, then change n2 n1 phi 1, n2 n2 phi 2, n2 n3 phi 3. Here n3 n1 phi 1, n3 n2 phi 2, n3 n3 phi 3, like this it will go on. And again I have made one mistake here, that is here I have made one mistake here. Because I have taken only 3 terms here, but why 3? It can be more than 3 also. It depends on your elements. So I am this is surely yeah. So this is the correct one. Okay. So the first term, that is this, yeah. So this is the first term. This is the first term. This is the first term, that is this term. That is, this is the initial notation. This is the matrix notation. In matrix notation, this one is in matrix notation, and this one is in indicial notation. Indicial notation. So this matrix we call it as KE, that is the element stiffness matrix. This is the force, this and this is the force vector due to F term, and this is the force vector due to boundary G term. So see, for G term the integration is over S2E, and for this is the integration over the domain, and this is again from the boundary. This is the stiffness coming from the boundary because phi j is there. Once this is multiplied by phi j, that means it is a stiffness term. So this is k is to e. So this is one stiffness term and there is another stiffness term, and stiffness term is always multiplied with phi j here. So we get one stiffness from the element. So where is it gone? So we get one stiffness from the element and the other stiffness from the boundary, and this is the force vector. So this is how we get the finite element equation. Now we are studying the same quasi-harmonic equation. The only difference is that now this is the domain. Over the domain, it's the 2D domain now. So this is omega. So this is in omega, and omega is now a 2D domain. Omega is now a 2D domain, and in the boundary condition, so we have taken actually a 2D quasi-harmonic equation. So this is a 2D case, and we will derive the corresponding finite element equations using Galerkin method. Okay, and again for the sake of simplicity, to keep the things simple, so this is the Dirichlet boundary condition S1, and S2 is the Cauchy boundary condition. We have not considered the convective term. You know, the convective term is H, which is a function of x, y, z to phi. So this is the convective boundary term. We have not considered the convective boundary term on S2, just for the sake of simplicity. So now you know in Galerkin's method, the equation has to be multiplied with an weighting function. So here, and we take the shape function itself as the weighting function. So ni into this whole equation, this has to be considered in the left hand side as minus fxy, and the right hand side should be 0, and that the whole left hand side has to be multiplied with the weighting function, which is ni. But we are just multiplying the first term, because whatever we'll get from here will be applicable for the second term also, and this term is relatively simple. So here you see, if you take ddx of the whole thing, here we have shown it, then first ddx derivative of the first term, the second term remains. So this is the second term and this is the first term. So the differentiation of the first term kx and second term remains as it is. Now this is the first term and this is the differentiation of the second term. And in Gauss divergence, and here we require a little bit of Gauss divergence theorem. So in Gauss divergence theorem, we know that if for a vector v dot n, where n is the outward normal of the domain, so if this is the domain omega, then this is n. So v dot n ds is divergence v d omega. So that means vx nx plus vy ny plus vz nz ds. ds is the element of the surface. This is ds, ds, and this is the whole surface is this. This is divergence v. And also you can show that this term is equal to the first term, this term is equal to the second term, and this term is equal to the third term. So that is what is shown here. So now see, now del x of this, so here we are starting again. So this minus this we have already seen, we are just repeating it because we have changed the page. So to keep the continuity, we are again repeating it, and here we are getting this term. So this del x, if we consider this as Vx, if we consider this as Vx, then this is Ni, this Kx, this dot Nx. So this is Vx Nx ds2, and that is actually the first of this del Vx del x. So del x, this is del Vx, so this is Vx, so del Vx del x is equal to Vx Nx ds2 minus this term. So now one question is, why S2? It should have been S, the whole domain, not only the Cauchy domain, whole surface, not only the Cauchy surface, not only the surface where Cauchy boundary condition is prescribed. So actually what happens is, on the this should have been ideally S, but we will be writing only S2 because on S1 that there is Dirichlet boundary conditions, and on Dirichlet boundary condition phi is known, and in finite elements that means all the nodal values of phi are known, and for known nodal values we delete those rows and columns. So it's so whether you keep it or you leave it, it's immaterial. So we will leave or we will not consider the terms on S1e. So we will only consider the terms on S2e. So that means this. So now if you combine, so we have taken only the first term. Now if you take the second term also, so that means if you start with this first term and second term minus f and all three multiplied with the weighting function, then here for this you would get this. So this from the first term and this from the second term minus this from the first term and this from the second term and this from the fourth term. So now if your element has no edge on S2 boundary, it means suppose this is your element. So this element has no edge on S2 boundary. S2 boundary is this. So then you need not consider this term, because again the row columns will corresponding to these are getting to be deleted. So you need not consider this term. Or if you have two elements with a common edge and the S2 term coming from this and the S2 term coming from this will get cancelled because the outward normal vector are opposite. So our outward unit normal vectors are opposite. So in these two cases you need not consider this term. What are the two cases? If element edge is on the Dirichlet boundary, if element edge is on the Dirichlet boundary, then you need not consider this term. If element edge is shared by two elements, then ignore cancels out after assembly, therefore can be ignored. Okay. Now if element has edge if the element has its edge on S2 boundary, then this term has to be which one? Yeah, then this term has to be taken into consideration, and you know kx del phi x del x nx plus ky del phi y del y ny from the boundary condition, you know that this is minus g. So we put minus g here, minus this equal to 0, and we make all of them positive. So this is the equation and this is the equation. Take first I equal to 1, then the first equation comes n1g, then n1, then all multiplications over j for x, all multiplication over j, del n1 del x, del n1 del x, del n1 del x, del n2 del x, del n1 del x, del n3 del x, and then this term n. Oh, here I have made a mistake. Oh, here I have made a mistake, because for the first equation this should be n1, n1. Yeah, this is okay. So this is, oh, so this, so first 1, here 1, then 1 2, then 1 3, then 1 4. For the second one, 2 1, 2 1, 2 2, 2 2, 2 3, 2 3, like this. And the fourth vector is simpler. So I think I have written this term twice. So I think we should omit this. So we should omit this. Where is it gone? Yeah, this one. So we should omit this term, because we have taken this term twice. So here it is, once we have taken it here, so we must omit this term. And it got, yeah. So, and we will bring this to, we'll bring this to here. Yeah, so it looks okay. It looks okay. So this is the equation. Okay, now okay, so let us stop here. Now let us see one thing, that, so this was our quasi-harmonic equation in 2D. And this was the Dirichlet boundary condition, and this was the Cauchy boundary condition. Sorry. And S1 plus S2 is S. So this was the equation, and deliberately we dropped this term. So had we not dropped this term, then what would have happened? Then actually we would have got your this thing ni, so kx del phi del x nx, or rather del phi e del x nx, plus ky del phi E del y ny, so to ds to E, ds to E. So here we would have got, now we have got only minus g. In the previous case we have got only minus g, and now we would get this, sorry, isn't it? So this is one extra term we are getting, which is ni h phi e, actually h phi e ds to e integral over s to e. So this is the term. Now see, since here one ni is already there and one phi e is already there, this would get a, this would give you a stiffness term, and that is actually s2 ni h nj phi j ds to e. Again the presence of phi j is there, that means this part will give you a stiffness term. So now if you write it in matrix notation, so this is s2e, and here you, so first one is n1, that is into here d is to e, and here phi 1 n1 n2 n2 n1 n2 n2. So this is actually the stiffness term which we call ks2. So now that means now your equation is k e plus k s2 phi plus r equal to 0. So this is the stiffness due to the convective boundary.